Hi, everyone. I'm Jason Mancuso, and I'll be talking about protecting sensitive data and machine learning models with CAPE privacy. So just a brief introduction, or I guess an overview of the talk. I will mainly be talking about confidential computing today. If you've heard of that or not, it's okay. I'll then kind of demonstrate how CAPE makes this possible in Python. Try to do a demo, and if we have time, talk about some extra features we've added that makes it a little more intuitive for Python users to use this technology. Who am I? I've been working at CAPE Privacy since the company began around 5 years ago, and my focus the entire time has been enabling what's referred to as privacy-preserving machine learning, or PPML for short. In the past, I've worked on applied data science and done some machine learning research. In CAPE Privacy, as a company, you may not have heard of us, but we kind of have an interesting backstory. We met all together online from different parts throughout the world just by working on open source privacy and machine learning tools. We have a long history of contributions to open source as the company kind of grew out of it. Here's some projects that we've contributed to or authored or maintained. PyCape is an educational PPML framework. It's very popular. We're the authors of TF Encrypted, which was a library built for running TensorFlow on encrypted data with secure multi-party computation. We'll talk about that a little bit. Also Moose, which is a rewrite of TF Encrypted in Rust, which was pretty recently open sourced. More recently, we've turned our attention to enclaves, and we've also done some open source work there as well with a project called Nitrogen that allows you to deploy arbitrary services to enclaves, and hybrid PKE, which is a Python library for using the HPKE encryption standard that's pretty recently been pioneered by Cloudflare and some others. I guess the long and short of it is that we really love machine learning and privacy. We think that the technology has the potential to really beneficially impact the world if it's handled responsibly. And in particular, we focus on privacy-aware machine learning. And because this is kind of different from how machine learning happens in the mainstream in a lot of cases, we believe that open source is critical for healthy adoption of that kind of technology. To cut to the chase, I would really love to get feedback on what you think of our product, our different open source projects, and everything we'll be talking about today, whether that's the CLI, the Python SDK, or the JavaScript tools, in case you're familiar with JavaScript. But also I'll provide links to kind of documentation, getting how to get started, and also a link to our Discord, where we can help you work through use cases or talk about supporting different things that you run into while using the project. But okay, so just to get started about how this stuff could be used to protect machine learning models and data, well, we kind of have to talk about the field of confidential computing as a whole. So what is confidential computing? Really, it's a broad set of technologies that is all about protecting data while it's in use. Now we have encrypted data. Data is often encrypted when we use it, right? Whether we're working in a browser and we're communicating with other web servers over HTTPS using TLS in the browser, or we're actually storing data and encrypting it in our hard drive or in some other hard drive. Most of the data that we use is encrypted, which is a good thing. The problem is that there's a gap between those two kind of states where data is in transit and when it's being stored, and that's when it's being processed. So generally, you'll receive some encrypted data, you'll decrypt it, you'll process it unencrypted on some server, and then if you want to persist that data, then you'll store it. And usually that storage is encrypted, not always, depending on the implementation, right? And so, but this set of technologies is all about bridging that gap between when the data is communicated and when it's stored. The entire time it's being processed, if it were encrypted, we could kind of say that data is always encrypted the entire time that you as a developer are dealing with it. This would be a boon to security, but also to user privacy, because they could be they could trust that they don't even have to trust you. They can just know that because the data is encrypted the entire time, their data is safe. Now I talked a few about a few of these different techniques. CAPE uses enclaves as its core technology today, although that wasn't always true, but we'll see why. This is a slide basically just covering kind of the recent trends in machine learning. Obviously, with ChatGPT and other models that have hit the public spotlight, the capabilities of machine learning models have really grown dramatically over the past several years. But the way they grew or the way they improved so dramatically is just that they scaled up, right? That these models are much bigger, they require much more compute to run. And so this is kind of an important trend. If you're trying to make machine learning more secure, more private for users, it's a trend you can't ignore or fight against. And so in our past work, we were dealing with other techniques to privacy preserving machine learning, like homomorph encryption or secure multi-party computation. These are very kind of hardcore cryptography based methods. They're kind of like the gold standard in terms of security level and like kind of theoretical reasoning and motivation, but they're generally too slow and inflexible for like large scale use. And enclaves kind of have a better trade-off here in a few different ways. So while the homomorph encryption and secure multi-party computation, while these techniques have like theoretically really strong security guarantees, enclave security is actually sufficient for pretty much all threat models that you would see in the real world. If you ever talk to a security team, the threat model that they're using is much closer to the threat model that enclaves are solving for, which is all developers are authenticated. You have strong application security around your servers, and whether you're in a kind of firewall network setting or like a zero trust organization, it's all about kind of managing security at many different levels. Enclaves fit into that very well, whereas these other solutions kind of ignore all of that kind of infrastructure security and operational security. Another thing is that flexibility. If you want to run any program with homomorph encryption or multi-party computation, you have to rewrite it completely in a framework that supports that kind of technology, which can be fine if it's like a small function, but if it's a machine learning model that was just published at the latest machine learning conference that it took someone a year to build, it's going to take you 6 months at least to rewrite it in one of these frameworks if you're lucky, because the frameworks may not support all the operations you need. Whereas enclaves are kind of plug and play. You take a Python script, you drop it in the enclave, you run it. So it's a very appealing feature of this technology. And the last is scaling, like I talked about with machine learning models scaling up. Enclaves don't have any meaningful difference in terms of the performance. It's like pretty marginal. It's whatever networking is required to like get the data in the model to the enclave. And also, when you compare that to some of these other technologies, they can be an order of magnitude slower, depending on the program, depending on the actual implementation, et cetera. So obviously that doesn't really work for the latest and greatest machine learning models, right? So this is why we've kind of focused in on enclaves recently. I'll talk a little bit about the primitives that are required to do confidential computing, especially with enclaves. And so kind of the biggest thing is encryption and key management. So these are two features that are, if you're dealing with sensitive data, you're probably familiar with, but like in a way that you're not very happy that you have to deal with these, because it's pretty common, it's pretty important, but they're generally pretty complicated. With encryption, it's kind of a nightmare if you dive into it and you're not a cryptographer. You have to decide between what protocol you're going to use for encryption. There could be all these different configuration options with each protocol. Depending on what you choose there, the security guarantees might differ for the encryption. Also, different encryption protocols have different levels of efficiency. For example, a lot of CPUs have built-in instructions to run AES encryption, but not all of them. And if you don't have those instructions, it could be quite slow. Another thing is that these protocols generally don't dictate a wire format. So there's all these things that you need when you encrypt data, including maybe a tag in AES. In the case of AES, a nonce is generally needed, which is kind of like a unique random string that gives you enough randomness to encrypt safely, and also potentially auxiliary data that you include. Most of these protocols allow for that, but if you don't know how to include it with your encrypted data, then you're kind of lost as to like how to decrypt the data. And so a good standard wire format is needed, and a developer generally has to decide on this. It's not dictated by the protocol. And then lastly, different protocols have different levels of support with like other infrastructure requirements. For example, KMS compatibility. HPK is like a relatively new encryption protocol, but it's not supported by many KMSs at all. And so if you're at a company that uses a KMS for security reasons, you may have to choose whatever fits into that KMS infrastructure. So just to like kind of summarize all that, if you look at this small Python function, it's relatively small, but there's a lot of detail hidden in this block of code. And as a developer, it's pretty unclear what tweaking any of these will do. And even to arrive at this bit of code, it's unclear how much research it would take any kind of average developer to get there. So one of the philosophies behind our effort here is that we think encryption has too many choices for the average developer. These sensible defaults exist, but figuring that out is like really high effort and low reward because it's like a baseline level of reward that you need in order to deal with sensitive data at all. Implementation can be difficult and error prone, and ultimately devs don't care. They just want an opinionated library that works out of the box, that they can trust, that has sensible defaults, and that can scale to whatever use case they're going to need to do it with or to use encryption for. And the second end of that is key management, which gets quite complicated. A lot of different products to choose from. Even just in AWS, there's KMS and Secrets Manager. Knowing which product to use can be confusing for your average developer. So ideally, the library kind of integrates with at least one KMS and simplifies everything away. Developers should never really need to worry about key management. The fact that they do means that there's something kind of broken in the way we deal with encryption today. So these are two kind of aspects of dealing with sensitive data that are really important. But a third is where do you actually process it? And for us, Nitro Enclaves has been the solution. So CAPE is built on AWS Nitro Enclaves, which are kind of, you can think of it as like a black box attached to a AWS instance that any code that's deployed into that black box can only ever be seen from inside the black box. Anything outside of that black box cannot view what's being run inside it. And then, so not only do they give you this kind of lockdown container-like environment to run code in, they also give a feature called Attestation, which allows any user of that program to confirm that, okay, I'm actually running this program on this enclave, nothing's been tampered. It kind of dictates the supply chain of the code and the data that is running on the instance. Because the black box, you need to be sure that like that black box is running what you think it's running, and Attestation gives you that tool. So one reason we like Nitro Enclaves is that they're flexible. You can essentially turn any container into an enclave image file, and the enclave image file, or EIF, is what's actually deployed and run inside of an enclave. This EIF contains kind of a snapshot of the Docker image at the point at which the EIF was created. This includes the entire file system of the OS inside the container. So it gives you essentially as flexible an environment as you're going to find, which is a Docker image. What allows the EIF to be run so securely is that it comes with some metadata. The first piece of metadata is arguably the most important. It's the signature. This allows you to know where an EIF came from. When you build an EIF, you sign it, and that signature can be used to verify that, for example, I, Jason Mancuso, authored this EIF and deployed it, and so you know that it hasn't been tampered with. And then, so that governs like kind of who authored the EIF. The second part is these PCRs. These PCRs, it gets a bit technical, but the idea is that it gives you a measurement of the system at every level of the stack. So that, and then ultimately it's this kind of, these PCRs give you a chain of trust all the way to the AWS root certificate that AWS publishes, has a lifetime of 30 years or so. And so essentially what PCRs give you is a way to verify that, okay, I'm running this EIF on top of this enclave, and this enclave is running on this AWS instance, and this AWS instance was generated by the AWS hypervisor. So all of that, and then you finally sign each of those PCRs until you get to the lowest one, which is AWS's root certificate. So all of the trust kind of boils down to, do you trust this AWS root certificate, which is a very obviously strong source of trust. So attestation is that process that I just described. And the idea is every time you connect with an enclave and interact with it, the enclave will send you an attestation document that contains all of this information. So anytime you make a connection, you can verify what's running inside the enclave and how the enclave was spawned from AWS's infrastructure. Again, it's all signed by the root AWS certificate, which once that's verified, you can kind of trust the entire chain as well. Okay, so that's all like the primitives that you need to work with confidential computing, but it doesn't really tell you like how to do it. And CAPE is designed to do it simply as a Python developer. So to summarize the CAPE platform as it currently stands, it's a platform for confidential Python functions as a service. What does that mean? If we break it down, confidential, obviously we want to keep any data that we send into the enclave, we want it to be secure. So this means as soon as the data is captured, encrypting it, and in such a way that only the enclave can decrypt it. And if we can do this and we can solve kind of the encryption complexity and the key management complexity, then we've kind of solved the confidentiality aspect of what we want, the confidential computing aspect. Python functions. Well, why Python functions? Well, it's the lingua franca of machine learning. There's a thriving open source ecosystem. A lot of it based in, I mean, not just machine learning, but anything you can think of, right? And as a part of that open source ecosystem, you get all kinds of high performance computing libraries and things that can make up for the fact that Python itself is not always the fastest language. But Python, more importantly, is kind of a simple, accessible, and a flexible language. You can do anything in Python, right? It's a great language. And then the last part, as a service, well, what CAPE offers is a way to manage all this infrastructure automatically. So you don't have to worry about key management. You don't have to worry about provisioning instances. All you really care about is the function that you're running confidentially. You can just deploy that and run it at will. So we have a couple of verbs associated with this. Obviously, encrypt is one of them. What CAPE offers is that like sensible default library for encrypting data. It's offline encryption of arbitrary bytes. So it's really up to you how you want to encrypt your data or set up your data to be encrypted, I guess. The encryption is authless, so you don't have to be a CAPE user or authenticated with CAPE in order to encrypt data. So you can do it anywhere from any platform, any language, ideally. And so this idea of reckless encryption comes up. We think that users can, or anybody can recklessly encrypt data for consumption inside of a CAPE enclave, because based on all that kind of trust that I laid out, decryption can only ever happen in the enclave, which gives you a high level of security and therefore a high level of trust with encrypted data. But of course, in order to use encrypted data afterwards, you need to be able to run functions on it, run programs with the data that involve the data. So this is where deploying comes in. And our main language for working with encrypted data inside of CAPE enclaves is Python. And so what we do is we expose this kind of ability to deploy Python functions. We manage kind of the lifetime of the function. Our goal is to, once you've deployed a function, you should be able to run that function on any encrypted data or unencrypted data if you want to, any amount of time in the future. And it should be essentially immediate in terms of, it should be immediately available, highly available, I guess. And yeah, that gives us the goal of running Python functions on encrypted data, and that's what CAPE tries to solve. So we have several different SDKs or tools that you can use to interact with CAPE functions or encrypt data. Our idea is that you should be able to encrypt data in any language, but and then interact with CAPE functions from a variety of languages as well. So we have a CLI tool that's written in Go that you can use to encrypt data, deploy functions, run functions. We have a Python SDK where you can do all the same things. Our JavaScript SDK is a bit different. It's built for mainly just encrypting data. For example, if you wanted to encrypt data in a browser or on a website, our JavaScript SDK gives you the ability to work with that data end-to-end encrypted with any CAPE functions. And then Java, similar. You should be able to encrypt data in Java and work with it in an end-to-end encrypted manner as well. More coming, including Rust is another one that we recently have been working on. Okay, so of course, everyone here is interested in Python, so let's talk about PyCape. PyCape is our Python client for interacting with Cape functions and encrypting data. You can get it at the link, the GitHub repository. There's also a documentation site that's written just for the Python library. Because it goes in, because our whole thing is deploying Python functions, confidential Python functions. We have some extra features in our Python SDK that aren't available in any other library, because really we have tools that make it easy to write those Cape functions in an ergonomic manner. Most of the Python client is written in Python, although there's some stuff in Rust. Mainly the encryption parts are written in Rust, because it's good to have, when we're talking about encryption, it's good to have like kind of one source of truth that's been audited to make sure that the implementation is correct. And so a lot of that stuff has happened in Rust, because the Rust has a very active cryptography community working on that kind of thing. But we use Python bindings for all of that stuff anyways, so that you as a Python user never even really realize you're using Rust in the background. Our main unit of kind of the thing that we care about is these Cape functions. Ultimately, what this boils down to, it's very similar to AWS Lambda if you've ever used it. Essentially, what we require is that you provide us a script called app.py, and somewhere in that script, there's a function called cape_handler. That cape_handler has to be a function that maps a single byte string to another byte string. But other than that, you can do anything you want inside of that function. This can call other functions. This can import stuff from other modules. This can turn these bytes into whatever it wants to, into whatever complex data structure you want, do whatever you want with it, pack it all back into bytes and return it. But the directory that contains this app.py file and any of its dependencies is the thing that is uploaded to Cape. Collectively, this directory is what we're really talking about when we talk about Cape functions. Okay, so it's a little easier, I think, if we walk through a demo. I think in the interest of time, I don't know if I'll be able to do the demo. We'll see. We'll try to do it. So this is an example of confidential image classification. The idea is that some client, whether it's another Python script or a web browser, like a web application in the browser, is collecting some image data, hopefully encrypting it, and then submitting it to some Cape function that's running in an enclave. That Cape function will classify the image using a pre-trained ResNet 50. It'll actually use the Onyx runtime to improve performance and reduce the dependency size, so we don't have to have all of like TensorFlow or PyTorch inside the enclave. And so let's do it. So the idea here is, well, we're going to need a few things, right? The first is a function that we actually want to run. In this case, here's a function that does what we want it to do. Just to go through this a bit, it's going to load an Onyx model, pre-trained ResNet 50, into an Onyx runtime session. And what this Cape handler function does is it takes some input bytes, interprets those as a NumPy array that has this shape. Essentially, this is an image. It turns that NumPy array into kind of inputs for the Onyx session, runs the Onyx session, and then from the outputs, it's going to get the top 5 classes and kind of format it nicely into a JSON that we can dump back into a byte string. And actually, so technically this is returning a string, but if it's a string, it'll just automatically convert it to a byte string with UTF-8. So that little detail. So the only requirements that we need for this are the Onyx runtime, technically, and PyCape. To actually download the model, we'll just use PyTorch, so that's why that's included here. But it's really not needed for the Cape function itself. So here is a script that we're going to use just to download the Onyx model. So I'll do that real quick, just to, Of course, you need a Conda environment. That should be it. Now I can download it. Okay, if we look at the Onyx model folder, yep, there's our Onyx model. It's about 100 megabytes. The next thing we do is, so I have the Cape CLI installed and I'm logged in. The login process is very simple. You just confirm that this code is displayed on your terminal correctly, which it is. This will then take you to GitHub to authenticate as a GitHub user. I've already done that, so it just does that very quickly. So congrats, I'm all set. What I would do now is I need to start creating a deploy folder. So in this case, I'll call it Onyx ResNet deploy. And if I were to look at that, okay, I've already actually done this. So I want to build up this folder as if it hasn't been done before. So the first thing I want to do is copy my app.py that we were just looking at into this folder. The next thing I'll do is take that downloaded Onyx model and copy it into the deploy folder so that the Cape function can load it in the enclave. And the last thing I'll do is install any dependencies that I need to run this function. If we look back at the function, the only things we should need are NumPy and the Onyx runtime. NumPy happens to be a dependency of the Onyx runtime, so we can really just install Onyx runtime and get everything we need. So the way I'll do that is a little complicated, but this is because, so most Python functions, or most Python packages, sorry, have C extensions, and those C extensions are usually delivered in a Python wheel as binaries. Those binaries have to be compiled for a specific architecture, right? Whether it's if you're on Mac, Mac OS, generally those binaries have been built for Darwin OS. If you're on Windows, there'll be differently compiled binaries. If you're on Linux, different Linux flavors can potentially have different binaries as well. So in this case, we're going to install the dependencies to that folder that we created, that deploy folder, inside of a Docker image that is based on Debian, a flavor of Debian called Bullseye. The idea is when we install the Onyx runtime and its dependencies, any binaries that are going to be contained in those dependencies, for example, the NumPy binaries or the Onyx runtime binaries, they should be, pip will try to find the one that's associated with that's compatible with a Debian platform. And so that's what this line does. I won't run it because I already did, but hopefully that gives you the gist of what it is. Because I'm on Linux, I probably wouldn't need to do this. I could probably just install the package into that folder, and because yeah, my architecture is similar to the one that's running in the enclave, then it would work. But it's not always true, so that's why we include that there. And so yeah, now that we have everything, this is what it should look like. It includes the app.py, which has your Cape function. Oh yeah, there's also an ImageNet class, classes.txt, which just has a labeling of all the ImageNet classes so that we can map from ImageNet class IDs to actual like human readable terms. And so we'd include that as well, just for our function to be able to return kind of a nice output. But once I've done all that, I should be able to find everything here in this deploy folder. If I look, it's got a lot of dependencies. It's got the Onyx model we downloaded, ImageNet classes that I mentioned, the Python function itself, and app.py. So now we have everything we need to deploy. Deploying is really simple. It's cape deploy and then the folder name. Because this is about 150 megabytes, it's not that big, but I've already done this just to ease the tutorial, but this is what you would do to actually deploy your function. Checking the tutorial, the next thing we would do. So there's a couple things. This will give you a function ID, a function checksum, and a function name. And those are basically just identifiers that allow you to make run requests against the function once it's been deployed. The ID is just an identifier. The name is also just a human readable identifier. The checksum is a little bit different. What this does is it gives you kind of an additional layer of security over attestation. So the Python SDK implements attestation, so you don't really need to worry about it. But this function checksum is just something you can do where it's generated locally when you deploy the function, and it's just a hash of the directory that you deployed. And so when you make run requests, you can pass this checksum at runtime when you're actually invoking the function. And the first thing that the enclave will do is check to make sure the checksum matches the deployed Cape function. So this is just to know that the function hasn't been tampered with or modified at all in between when you deployed it and when you're actually running it in the enclave. Attestation covers this in the case of deploying EIFs, but this is an additional layer on top of that for us. And so yeah. Now PyCape, because one of the main things it wants to do is that like authless encryption. It means that if you're running PyCape, you don't need to be authenticated with Cape. So in order to actually make any run requests, you'll need an access token. We can create that here pretty quickly. Let's see, with something like this. This will generate a token for 10 minutes and stash it in this token variable. I won't show it because then this is kind of a sensitive thing, right? Anybody who has this token can call functions that you've deployed. So because I don't want that to be true, like I'm not going to reveal it to anyone. And so when we actually call the function from Python, let's see. I'll show the. First of all, let's take some data and encrypt it. So this is just a Python function that's going to encrypt some data. What you get out is this string here. It starts with Cape, which is just a prefix that lets you know that the rest of these bytes that you're seeing are just encrypted bytes. And yeah, the rest is it's called an envelope encryption. It's your data encrypted with AES and then encrypted again outside of that with RSA. But that's the details of the encryption protocol that we use, which is kind of it's in our documentation if you're interested. But this Cape encrypted blob is something that you can use as input to Cape models. It doesn't need to be this way. You could just pass raw bytes, but this allows you to build applications that are end-to-end encrypted from when you collect the data to when you're running it inside the enclave, and even when it comes back out, you can keep it encrypted as well, whatever the output is, if you want that to be true. So now I'll look at this last file, which is run encrypt. What this does is it pulls an image, this dog.jpg, very cute dog, and reads that image into memory, turns it into a NumPy array, converts that NumPy array into bytes, and then encrypts those bytes with Cape encrypt. And I'm encrypting for my own username here, but in general, you would do that for whoever owns the function that was deployed. And then when you actually call Cape run, you have a function that references the function that we deployed. In this case, it's the Onyx ResNet deploy function that we just deployed. The token, which is the thing that allows you to call that function, and the encrypted bytes, which is the encrypted dog image. And so we'll run that function, we'll get some bytes back, we'll interpret those as a JSON. Then in that JSON, we'll look at all of its contents and just print those contents to the terminal. And so if I do that now, sorry, I forgot to actually run that. So now the token is actually in okay, I guess that was that. Maybe I'll have to do this real quick, just so we know. Well, okay. I guess I made a mistake with my token somewhere, but that's on me. In any case, when you run it, you should be able to see this output from the model, which is the top 5 classes for that image. Man, now I'm curious. Now I want to go and debug that. But anyways, that was the demo. Feel free to try it out yourself because if you follow those steps, then you should be able to reproduce it on your own machine if you've signed up for Cape. And so I definitely recommend doing that. So these are some extra features. I don't know if there's time. There's a little bit of time. We can talk about it. So here's some extra features that we've had in the PyCape SDK in particular, which are kind of like helpers for building Cape functions. The first one's called Serdio. Now, I talked about these Cape handler functions, which are functions that map byte strings to byte strings. But most functions you use in Python are not mapping just bytes, raw bytes to raw bytes, right? Python is a very high level language, so you're rarely working with bytes. So the idea of this library is to make that more fluid for you. If you have some function that takes some arbitrary Python function or arbitrary Python signature, Serdio gives you a way to seamlessly convert that to a bytes handler very quickly in a way that it doesn't modify the original function. So you can still use the function as normal, but the resulting bytes handler can be used in Cape. So the idea of this is just to remove some of that overhead of like you're dealing with all these Python objects and all of a sudden you need to switch into bytes, and then in your Cape function you have to switch back from bytes into those original Python types. This makes it super easy, so it's just all automatic. Here's an example that's a bit more related to the example we were doing, where this Cape handler takes a NumPy array and produces a NumPy array. Because NumPy arrays aren't raw bytes, we use Serdio to automatically turn those NumPy arrays into raw bytes and then back. And we do that with like a small helper function because NumPy arrays are not native Python built-in types. So we need to direct Serdio as to how to turn those into native Python types. But that's all you really have to do to work with it. And it makes these functions much easier to use, much easier to test, and a bit more foolproof. Another thing we do is fine-grain encryption and decryption inside of the Cape function. The idea here being that, well, if you're just supplying an image like we did in the demo, and it's encrypted, that's fine. Cape will automatically decrypt it as soon as it sees it. If it'll look at the byte string that's being passed into the function. If it looks like a Cape encrypted blob, it'll automatically decrypt it using your key. And the details of that are kind of abstracted away in the key management system, but it's linked to your user account. But the question is, what if this data is not just a single encrypted blob, but it's a more compound data structure, or like kind of the bytes are, for example, if you're using the Serdio and it was a NumPy array, or if it was a collection of different arguments, some of which were encrypted, some of which aren't, how would you deal with that? And the idea is that you have access to the decryption function inside of your Cape function. So because the enclave is the only place you can decrypt data, we give you manual control over that if your input data doesn't conform to that like single bytes input. And so, for example, here we have some data that's actually JSON bytes. So this potentially includes plain text data and encrypted data. And so you just look for the encrypted field in the JSON and manually decrypt that. And now you're working with the plain text of that encrypted data. This is also super helpful for when you're trying to write an application that collects encrypted data from multiple different clients. For example, if you had a browser that was collecting data for different users and encrypting it in the browser, then you pass that to some server that's going to launch kind of a subroutine that's confidential. You wouldn't have to decrypt that data on that Python or on that server. You would just pass the encrypted data to the Cape function and then manually decrypt each client or each web browser's encrypted data inside of the enclave, and then do whatever you needed to do with it. And yeah, so that's this tool allows you to do that and build multi-party applications in a way that's end-to-end. So yeah, that's actually everything I have. Thank you for sticking around and for listening to the talk. Here's some links to our documentation and our Discord. Like I said, we're always around. We're always happy to talk about how people are finding this stuff, how they're using it, or aiming to use it for their own applications. And yeah, thank you for your time.